Hi everyone, and thank you for watching this video. My name is Ivo and I'm a solutions architect and computer science educator. This is episode 2 of a video series presenting a proof of concept to connect and monitor a smart factory using a Matter controller, the AWS cloud, and a React-based management server. In the first episode, I provided an end-to-end overview of the proof of concept that I built, starting with how the new Matter standard can help with interoperability in a fictitious smart factory. I then walked through the proof of concept architecture and I showed you a demo. In this episode, we will deep dive into the AWS IoT Greengrass-based edge solution. In the last episode, we will delve into the CI/CD process for the development, integration, and deployment of such a solution. So let's briefly recap on the key features of the Matter protocol. So first off, it's a unifying connectivity standard for smart devices, and it's backed by the industry. It's supported by the major tech firms, which ensure its relevance and integration into the major ecosystems. It's based on IP, which has all the benefits around ease of integration and monitoring. And it's based on an open source approach, which will promote innovation and ensure widespread adoption. It's scalable and reliable, and it's adaptable to a variety of demands, ensuring consistent user experience. But Matter extends beyond the smart home, finding uses in various industries such as healthcare, industrial IoT, smart retail, etc. But the key thing we're going to focus on this video is Matter in an industrial context. Matter security and interoperability features make it ideal for industrial IoT. In order to support industrial IoT use cases, we need an industrial IoT Matter controller. This features a CPU-based embedded system with a Linux-based OS for protocol translation between Matter and the cloud. This is designed for easy deployment, zero-touch provisioning, and updates. And it offers offline operation and resilience, and it will be able to operate offline and be resilient to reboots and outages. And it provides both supports for local and cloud. In episode 1, we learned about the overall architecture of the proof of concept, and we saw a demo showing the Matter controller controlling Matter-enabled accessories using the Matter protocol and the features of the AWS IoT cloud. In this second episode, we will look at the architecture of the edge solution. We will examine both the standard AWS and custom Python Greengrass components, and we will also learn about how the system offers offline and reboot resilience using the disk booter Greengrass component. In the third and last episode, we will dive into the CI/CD processes and procedures for streamlining DevOps and field deployment of the overall solution. So let's look at the edge solution architecture. Nucleus is the core and mandatory component of the AWS IoT Greengrass core software, providing the base functionality in terms of the component deployment, orchestration, and lifecycle management. And I'm using version 2.11.3 at the time of this recording. You should check for a more recent version and use the latest available. The 2.11 version introduces the support for a new component called Disk Booter, which is an AWS provided component that offers the option of persisting all the MQTT messages on disk from the Greengrass core device to the AWS IoT core. I'm using this component to make the solution resilient for not only upstream network connectivity issues, but also for system reboots caused by power outages or other such failures. I also developed a Python-based custom component that uses WebSockets to communicate with the Python Matter server. The Python Matter server interfaces to the Matter-enabled devices using the Matter protocol. This server has a built-in Python-based wrapper to the Project Chip Connected Home over IP SDK and exposes all the Matter interfaces using WebSockets. The Python Matter server is deployed as a pre-built Docker container using the Greengrass Docker Application Manager standard component. To locally manage the solution, a React-based admin server is also deployed using the Greengrass Docker Application Manager. This React-based server also mimics the AWS API gateway and provides local REST-based endpoints to query the IoT shadows via the IoT Shadow Manager component. This removes the need for the local admin server to query the API gateway in the cloud. The state of the Matter-enabled endpoints is mirrored in IoT Shadows. The IoT Shadow Manager also provides the synchronization of IoT Shadows to the AWS cloud. This enables the cloud-based admin server to securely read and update the state of the Matter-enabled devices via the API gateway. And I consider all of these components part of an overall greengrass deployment that I want to be deployed to all my Matter control devices. Therefore, I defined a greengrass deployment which targets the thing group named MCC thing, and at provisioning time all my devices will be assigned to the MCC thing group, and they will automatically get this deployment on all these components. During the operation of the Matter controller, the custom component can receive MQTT-based commands from the IoT core over the Inter-Process Communication (IPC), and changes made to Matter-enabled end devices will result in changes to IoT Shadows. Changes to IoT Shadows will result in MQTT messages that will be sent over the Greengrass IPC. So let's see it all in action, and let's jump over to the AWS console. So we're over here on the AWS IoT cloud, and if we look here we have the thing groups, and if we look at the thing groups here, you'll see we have one thing group called MCC thing, and this thing group will be this target of our deployments. And you can see here within this thing group we have one thing, the MCC thing version 1. Now this thing here has been set up, it's a subject of being a Greengrass device. So if we look over on the core devices here, we'll see that this thing is also a Greengrass core device as well. And this Greengrass core device, you can see when we click into it here, you'll see it has a number of components and it's part of this MCC thing group. And if we look at the deployments that are generated on this, we have a deployment called the MCC dev deployment. So let's just click in here and have a look at this deployment. So in this deployment here, you can see we have several components that are deployed, and we have the standard AWS components and the custom component that I developed for the Matter Cloud Controller daemon. So if we look at the nucleus here, it's important to point out that we're using the disk spooler, but one of the requirements is that you need to make an additional configuration to the nucleus component in order to set up the disk spooler to use the disk storage. So this is done as a configuration on the nucleus one, and you see here we have MQTT disk spooler storage type disk. So that's important to do that so that the MQTT messages are persisted on the disk. So you can see now we have the main components here. The main custom component is this MCC daemon, and this component here is the one that has the Matter Cloud Controller. And you'll see here that it has a dependency on the Docker Application Manager, and you can see here the lifecycle script that we use. So when we initially start up, the first thing that will happen is that we'll install the various requirements. Then as part of the run, we will use Docker Compose to pull in the latest API and web Docker containers that hold the front end. Then what we'll do is we'll bring these Docker containers up, and once these Docker containers are brought up, we will then run the Matter Cloud Controller Python script, which will then interface with the Python Matter server that's running in one of these Docker components. And you can see here that when we shut down, we bring down these Docker containers, we stop them then. And you can see here we have several artifacts that we have dependencies on. We're bringing in the Matter Dashboard API and web from the GitHub or the Docker Hub. And we're also using the Python Matter server. Within the actual thing, you'll see we have a certificate that is set up, and this certificate has been provisioned when we run the install script, and the policy on this allows this Matter Cloud Controller, this Greengrass device, to interact with the shadows and also to subscribe and publish onto the IPC. We can see here on the things, if we go into the things thing and then we look at the device shadows, the device shadows are a mapping to the endpoints on the actual end device. So we have an endpoint 0 and an endpoint 1. And here you can see on endpoint 1, this is for one of a smart plug that I have plugged in at the moment. And you can see here, for example, one of the attributes is endpoint 1, cluster 6 and attribute 0, which is the state of the plug, which is true. So as you can see here, this JSON format here captures the current state of the Matter devices. Now we have a set of rules that we have set up here as well. So if there's any updates to these shadows, then we will catch it with this rule here. So we'll look at for an update to the shadow. If the update has been accepted, what we'll do here is we'll pass on the details of the update to the SNS, the simple notification service. And this simple notification service is mapped to a Lambda function, which will go and process these changes to the shadow state. So if we'll have a look here, it's a Lambda function here, and we'll just go and have a quick look at the actual Lambda code for the Lambda function here. So the Lambda function that we use when a shadow is updated is called the update shadow Lambda function. We'll see it here. This is the update function, and we have a quick look at this function here. This code is populated automatically by the deployment process that we'll talk about in the next video. But just a quick look at this code here. This code, all it does is it connects to a database and it processes the JSON message that comes in, and it then will cache all these JSON messages to the database. So all the attribute changes will be put into the databases as soon as a shadow is updated.